Okay, so welcome. So this is uh, today we're going to continue where we left off about convolution neural networks. Um, and before that, I wanted to make a few announcements. First thing is there is a Slack workspace that I created, and I'm just going to paste the invitation link here. You can access it, and last time there was a request for setting up a Slack channel, so you can access it and register yourself. So currently it's just Teng Teng and me in the workspace, but if you guys want to use that and reach out to us in that way instead of email, that's fine too. Okay. Second thing is that I set up a discussion board on Blackboard. So yeah, so basically it's a very, it's nothing going on at the moment, but basically you can use forum and you can start, you can create thread and so on as if you have questions that way. Okay. So, I mean, you can certainly ask questions to other students through both of these media. Okay. Um, those are the quick two announcements about Slack and about discussion board. The third quick announcement is about, uh, yeah, is about annotated slides. I think last time somebody asked, um, uh, so if they can access annotated slides. So the link is here. So it basically uses SharePoint, or basically it's what I'm annotating in is basically a OneNote notebook. So as long as you have UIC email, you should be able to access these notebooks. Okay, so you can do a read access and look at the annotations. So very related to that, I added one more reference here called Deep Learning for Coders with Fast AI. Fast AI is a package which complements PyTorch, and it's focused on more, I would say, programmers who don't want to talk about models first, but also they want to first get started with a code base which works and does something, which uses deep neural networks under the hood, and then they explore how do they work and how do they tune them and so on. So it's a slightly different perspective of going through the same material, useful for folks who are programming or coding oriented. Okay, so that's a announcement related to that. Yeah, and finally about groups and assignments and projects. So far, I think given the shared notebook that we have provided, that we have, everybody seems to have filled in their names either as a single person group or two-person group. That's great. And I guess that was necessary for the first assignment. So now that the groups are there, I strongly encourage you to start thinking about project ideas, so that you have something concrete to talk about when we get to, in a couple of weeks, basically, or in 3 weeks, I guess. So talk to your teammate, and if you have multiple choices and you're unable to decide on something, you can contact me or Teng Teng. One, I guess, quick advice is I would suggest not picking image captioning as a project because it's very common, and I would say it's so common that I think it's good to explore something else. Okay. um, yeah, and I guess I'll start with the discussion or logistics part by quickly asking you guys a question about how was your first assignment submission. So was everybody able to complete in time?
I mean, this is George, by the way, but I
Mm-hmm.
can tell you that we were able to complete on time. I mean, the last question in there was the most intensive in terms of coding that we found, and the last one, I mean, my teammate, right, CJ may have more opinions,
Mm-hmm.
but we were thinking that I mean, it took a lot of time to execute
Yes.
the code and understand some of the various patterns that were coming.
Yes. Yes.
Um,
Yes. Yes.
that is one part. The other part is the ReLU versus the leaky, RELU.
Yeah.
I mean, that is one part of the metrics. The other part of the metrics, a low number of the density versus a high number of the density. We were not exactly sure why the patterns came. We tried to research quite a bit as to what it is. That is something that.
Yeah. So I think so. This was just an exploration because this is design choices that people have to make, and people have figured out what is the right choice to make. And we'll see today for convolutional neural networks, there is some choice, something equivalent to the number of hidden units that folks make, and we'll see when we talk about convolution layer today. But many of these choices are, driven by empirical performance. But it was just a question about, hey, how does your, what is your impression about model performance, model training performance, or model performance on held out test data based on let's say the number of hidden units. Okay. So it's just I think it's a little bit of an open-ended question here. Yeah.
Right. Just adding on to what George said, my teammate here. So I think that when we were doing this, we had to also do a lot of additional research in terms of like the documentation of what Keras was, of TensorFlow, and things like that.
Yes, exactly. So Keras is just it's currently now just part of TensorFlow. So it's not really that you do anything in TensorFlow, but yeah, you need to install TensorFlow. I mean, you'll have TensorFlow if you do it in Collab, but yeah, Keras-based definition of this two-layer feed-forward network is something that we have not seen in the lectures. But yeah, that's a great question. Yeah, I mean, in this sense, that's a great observation. That's a latent work that you need to do for this question. Yes. Yeah.
Okay,
prep work is needed, and I hope that this, this is just, I guess, from their tutorials. So I hope that gave you some sort of a template to at least study how they lay out an example, deep learning training script, right? So they'll do some loading of the data, for example, setting up the data, and define the model is the easiest actually in Keras, but and then there's the whole training loop and so on. So, and also handling this data is depending on how you handle it is going to be non-trivial. So, I mean, some of you must have seen MNIST data from before. If not, this is, I guess, the first exposure to a non-trivial data set. Because in the class so far, we have only seen a trivial data set, right? A two-dimensional data set. Yeah. Yeah, I think I hope there was some exposure to Keras through this question. I understand there were several parts in many of these questions, but hopefully this should make the next assignment a little bit easier, where the scaffold, which is like setting up a deep learning training notebook, should be very similar, but in a similar pattern. But what's going to change is the model, for example, is going to change. Okay, depending on what the appropriate question next time. I think there are only 2 questions, I believe, but we'll get there. Good. So if there are more questions, let's discuss maybe after the lecture of your impressions on this assignment. Let's get back to where we left out last time. And before I pick up the slides and start writing something, let me just go over again where we are in the trajectory. As I said, the sessions don't correspond to exactly the unit of like lectures or whatever modules given here, but that's okay. We want to get, so I want to spend sufficient time on the basics, because once you see the base algorithms, or sorry, the base models in dealing with images or dealing with text, I think the more complicated models are just, are a little bit easier once you really understand in a thorough sense the basic models. Okay, so what we saw, feed-forward neural networks are something that existed for about 40 years now, 30 years, or even more actually. But they form the basis of a feed-forward, I guess, a fully connected layer, and we'll see that today. What we'll see today, we'll continue on about convolutional neural networks, and we'll see the most vanilla version of it. Okay, so we're going to really drill down and say, hey, here's a convolutional layer. It's not very different from a fully connected layer, and so on. But you'll see that the research papers as recently as 2017, 18 are pretty much playing around with the convolutional layer and the fully connected layer in various ways to get bumps in image-based prediction problem performances, right? For example, classification, or could be other things in this area. So this is a basic building block. We're going to just look at the vanilla convolutional neural network, basically. And so in that sense, last time we looked at, for fully connected layers, we looked at what's hidden layers, what's nonlinearities, what's meant by hidden units and all that. And then we jumped over to just started discussing about convolutional neural networks. And there I said, hey, to think about convolutional neural networks, we just have to change our this diagram of the model. Okay, so for any neural network model, it's generally people write a layered diagram. Okay, it's not exactly the computational graph, but it looks like a computational graph, where in each layer there's some computation happening. In each layer there are some hidden units or hidden neurons or nodes that do some sort of a linear, some linear computation. Okay, so there was this layered view, and for convolutional layers, we said, hey, there's going to be that layers look like cuboids. Okay, or tensors, and that's where we kind of stopped, and we'll now spend the first half of the session at least to really unravel that quite a bit. Okay, and then we'll also look at pooling. That's the second type of a layer, you can say. It really doesn't have parameters, although you can introduce parameters. So we're only looking at the vanilla version where there's no parameters. So we look at pooling as a operation, as a kind of a layer operation. And then, towards the later part of the session, we're going to look at some, once we have the base idea of, hey, here's a convolutional neural network, we're going to look at a couple of key ideas. One is the notion of transfer learning, okay, which is very critical and which led to the success of this image-based, led to the success of convolutional neural networks or deep learning in general this past decade. Okay, 2010s to 2020, it was all about hey, we have a lot of data, we have GPUs, let's train neural networks, but let's also use pre-trained neural networks in other tasks that it was not trained on. Okay, that's the idea of transfer learning. And so we'll look at what transfer learning really means. And it's a very intuitive concept. So let's look at transfer learning. That's one of the goals. And then we'll also look at a few more engineering tricks. Okay, so first part will only focus on vanilla convolutional layer, and we'll only look at what's the layer, what's the conv layer, and what's the pooling layer. But there are a few additional engineering tricks. I wouldn't say engineering tricks, but I would say new, additional bells and whistles that people have figured out that kind of really help defining such a neural network model in terms of like performance, basically. And so, for example, there's something called dropout. It's like a regularization, so it's like very similar to the like the regularization that we saw in the linear multi-class, in the multi-class logic regression model that we saw earlier, or even the models that you have worked on in assignment. So instead of that type of regularization, there's a slightly different type of regularization that was introduced a few years ago, and we look at that. That's called dropout, and some additional tricks. Okay, so the thing about these tricks is they may get outdated. Okay, they may get updated, but it's good to see a few tricks to see how they work. Okay, and yeah, and then we'll also see how to let's say we trained a CNN model and it has some performance. Let's say it's just doing binary classification. Let's say it's doing cats versus dogs. You already have a model. How do you diagnose that model? Okay, so I know some of you have done 572. There was recent emphasis on, hey, once you train a model, maybe you can look at feature importances, or you can look at, for example, statistical significance of the coefficients in a linear model and things like that, right? So there were some diagnostics that you would do, like, for example, plot terrestrial or QQ plots and things like that. So so there may be many different diagnostic steps that you can take once you have trained a model. So we'll look at, I wouldn't say it's exactly the same class, but it's an informal way to really understand whether your model has really picked up the right patterns to, let's say, classify or predict or whatever. Okay, so those are the goals. Maybe we'll not cover everything here, but let's get started with where we left off on convolution layer. Okay. I hope the lay of the land is clear. So we are looking at, mostly we're looking at image data for the whole session today anyway. For images, we're just looking at a new class of models that we started last time, the convolutional neural network model class. If there are no questions, then I'm going to jump over to the slides. Okay, I wanted to actually let me continue sharing this. and actually give you a link before I jump over to the slides. This is this link. It's on the chat, so folks can click on it. So the good thing about this link is it shows okay. So what it shows is okay, I don't think I planned this properly yet. Supposed to be fully connected network visualization, and this is not working properly. Okay, I think the simulation is not working. I didn't double check it properly. No, it is working. Okay, so actually I wanted to see if the linear model worked. So, okay, so the link I shared with you is a illustration. So this is a link. It's an interactive, visualization of CNNs. That's the primary objective, but they also have, so basically they have a set of 4 visualizations. Let's not worry about the 3D versions. I think it's basically parallel to the 2D versions. In the 2D version, so visualization number, let's say the last 2, one is about fully connected network. The other one is about convolution neural network visualization. Okay. It's good to see this visualization at some point. So I thought, let me front load it first and then talk about the conv layer. As we look at this visualization. Okay. So I don't know if, so let's draw some number here. Okay. So I just want you to see this visualization as like at least a very, I would say this is like a bird's eye view of that layered diagram that we have been seeing we've seen for the fully connected layer, feed forward neural networks. Okay, so for example, let's ignore the let's focus from the top. Okay, so you can see so this is actually the MNIST data. Okay, so you can see there are 10 classes and it's represented as a row. So this row here, so this number, I think it's quite, it doesn't zoom in. So I don't know if folks can see this, but I would suggest, you can open the link that I've shared on the chat. So if you look at the top, this is a 10-dimensional vector at the top. Okay, so you can see this vector with a bunch of black cells, and one of the cells is blue. Or turquoise. Basically, that cell is corresponding to the number 3. So I drew a number 3, and this network is trained, and so it's saying, hey, the number 3, has a high value, okay, and therefore it's not dark. Okay, so all the other cells are dark. So it's basically correctly predicting that this whatever I drew, or you can also draw, is number 3. Okay, so for example, I can draw, let's say 1, and you can see that it's it's highlighting 1. Okay. So now, so what is this trying to show? This, this whole visualization is trying to show which neurons have high values. And so let's focus on the top part now, because the top part is actually essentially corresponds to fully connected layers. Okay, so the output is a 10-dimensional vector. Okay, 10-dimensional score vector, and you can see that each score vector, score coordinate, is related to the previous layer. Okay, the previous layer, and all entries in the previous layer. So the previous layer is this one. So which is like so you can see there's a fan out diagram, fan out a bunch of lines connecting. Okay, so this this layer here is a fully connected layer. That's why you're looking at it as if it's a flat bunch of cells. Okay, so that's the layered view that we saw in the last lecture, or even the previous lecture. It was last lecture where each neuron is one below the other. So you can think of this as a fully connected layer, the one right below the score vector layer. The second one from the top is a fully connected layer. Okay? or it's the output of that layer. Similarly, that if you highlight any one of those cells, it's a neuron, because each cell in that layer, it's a long vector, but each cell, each coordinate is a neuron's output. And so there's a neuron corresponding to it. Okay. So that neuron takes as an input everything from the previous layer. And you can see that using, from that, that fan out of a bunch of lines going to everything from before. Okay. Similarly, the score vector is connected to everything from the previous layer, right? A score coordinate is connected to everything from the previous layer. Similarly, each neuron and in the second layer from the top is connected to everything from the previous layers, everything from the previous layer. Okay, so those are fully connected layers, and you've seen that before. Okay, so that's the layer view up to that point. We're going to talk about this bottom part now in the bottom part now. Okay, in the next few minutes. So there's a question, how did you enter the number in the box? I just use my mouse. So I don't know if, so it could be browser issues, but I'm just drawing it using the mouse. Okay. Yeah, it could be a browser issue. Actually, I thought all of them works. For example, for me, the fully connected layer did not work. Like this is supposed to show me just the 3 layers, but just the top part. Okay. For example, you can use MNIST, and you have actually used MNIST with the 2-layer neural network, or you could have 3-layer neural network, right? So that would just correspond to the top. If it's just a 2-layer neural network, it would just correspond to the top part, right? Like one hidden layer, for example, and one input layer, one hidden layer, and one output layer. That would be just the top part of this animation here. So Chaitanya is saying it works in Chrome, but some version of Chrome is not working. Sorry about that. But I think it's a good diagram, and we'll come back to this figure in a few minutes. Okay. So with that, let me share my slides. Okay. So so what we're going to do now, so just as a recap, where were we with PNNs? What we motivated last time, I'm just going to write a small recap because I don't want to spend too much time on the recap. So last time we said, hey, fully connected layers, there's going to be some input layer. There's going to be one, let's say we only had, like, for example, in the assignment, in the last question, you did one hidden layer or 2-layer neural network. So, and there'll be some output layer. Okay. So, for example, let's say this has this hidden layer has 4 neurons. Okay. And input, for example, could be 2 dimensions, and output could be, let's say, 3 dimensions. So this was the example code that we also had. Okay. And so because there were 4 neurons, this side had a yeah, so this side had and this was basically let's say 4x2, and this was 4+1. Okay. So you had a matrix like this. So basically a bunch of parameters related to, when I say this side, there's a bunch of edges, like for example, 2 edges this way, 2 edges this way, 2 edges this way, 2 edges this way. So those edges have weights on them, okay? And basically the 8 numbers on those edges. And each neuron also has an extra dangling bias or an extra, I guess, a scalar value or a single number associated with it. Okay, so each neuron, what does it do? It just takes, for example, I think we saw last time, so the 4 rows, let's focus on the first neuron. The first neuron, let's say, has numbers 2 and 3 for the W matrix, let's say W1, and B has, let's say, number, let's say 1. Okay, there are other numbers here. And so given x, which is, let's say, 5 and 10, you just multiply the first coordinates, the second coordinates, and then add the extra one. Okay, so that's what you would do. That's what the neuron would do, and then it will also apply a nonlinearity. Okay, so that's what we saw. Layered view. So sorry, let's come back to this layered view. From here, we said, let's now think about not vectors, but tensors. Okay? I also interchangeably call them cuboids. Okay? Which means that, and tensors make sense because image, for example, is actually a tensor. Okay, it looks like a box. It has some depth, which is 3, corresponding to the 3 color channels. And it will have some width and height. Okay, so width and height, and let's call this. A cuboid is an input, and then at each layer you can think of different types of cuboids. Okay, and let's not, I would say, anchor ourselves to thinking that, hey, each layer cuboid should also exactly have some depth of 3 or something. Maybe this depth is 100. Okay, maybe this width is maybe this width is 32 and height is 32 initially. Let's say 50 for 10 data. Maybe this width here is like 16, here it's still 32. It doesn't matter. These numbers are not related. I mean, they are related, but I'm just saying that ultimately this tensor will have its own bunch of numbers, okay, which define that tensor. How, whether it's a thin tensor, a very fat tensor, or whatever it is. Okay? And similarly, we'll have to think of, hey, after this, eventually, let's say there's only one layer in between, and this is and so this tensor will have a bunch of cells, right? So a tensor, for example, index whatever, in the x, height coordinate, in the weight coordinate, and then in the depth coordinate, each cell will have a number, right? So a tensor will have a bunch of numbers. So each cell will have a number. That number corresponds to a neuron. Okay, just like in this view here, each corresponds to a neuron, right? So there's a number computed here in this darkened red region that I showed, and that corresponds to basically a neuron. So similarly, each tensor will have each cell in a tensor is corresponding to a neuron, and we'll see what type of neurons they are depending on the layer. And particularly, we are introducing that new layer, which is the convolution layer. Okay. And finally, I said, hey, a score vector, let's say if it was exactly the 3, let's say the 3 class classifier, then the score vector will have 3 cells, 1 cross 1 cross, let's say 3 would be the dimensionality of this tensor. So it's a redundant tensor because you can't really, you can just say, hey, there's no one, there's no height and width. It's just basically depth of 3 numbers stacked like this way. Okay. And why this way? Why not, like vertical? It's just a convention, that's not very important. So this is where we stopped last time. And we said this layer is going to, once we got this tensor point of view of thinking of a model. Okay. So then we said this layer can be a con layer or a fully connected or a feed-forward, hidden layer is also a fully connected layer, or a pooling layer. Okay. These are 3 choices, and we'll introduce these 2 choices today. And when I say introduce these 2 choices, all we're going to discuss is, hey, how is that neuron? What does that neuron do? Let's say a generic neuron, because if the conv layer produces a tensor as an output, if I just focus on each cell in the output and say the neuron corresponding to it, what did it do? Then I'm fine, right? So if I can tell you what a generic neuron did in a conv layer, then we know everything what any neuron did in that conv layer. Okay, to get a tensor as an output. Okay, and we'll also see pooling, but pooling you really don't need. It's pretty straightforward. So we'll see what we'll see about it when we get there. So any questions about this part before I get into the details of the conv layer? Okay, so let's now start thinking about it. So this is the first concept. It's a little bit of a warm up, but also can trip up a few people. So there is going to be a few certain words, keywords, or phrases that are going to be used. Just think of this as terminology to describe this diagram of the model. Okay, so one can certainly write some mathematical symbol, just like writing a linear model is like saying, hey, x transpose beta or something, right? One can certainly write it that way and not think of this diagrammatic view of the model. But the diagrammatic view of the model really helps, okay, to conceptually understand how data is flowing through, how input is flowing through your model to get to your score vectors. Okay, so now here's the first idea, or here's the key idea. The idea is that each layer, as I said, you can think of the output tensor is related to a layer. So the tensor, so each layer is, each layer will have a bunch of parameters, just like the linear layer will have the parameter W and B, right? Each layer's parameters, the con layer parameters correspond to a set of filters. So which means that instead of thinking of W comma B, a weight matrix and some bias vector, we'll think of, there are a bunch of parameters, we don't know how to, let's not give the name W and B right now, but we'll say, hey, there's a bunch of parameters, but we'll collect them into sets. Okay, so let's, put like 10 parameters in one set, 10 parameters in another set, 10 parameters in another set, and so on. And these sets are going to be called filters. Okay, so that's the that's the name given to these sets of parameters. Okay, and what is a filter? It's a as I said, it's a bunch of parameters, but at the end of the day, these parameters correspond to a function by themselves. Okay, and so what is that function? So because remember in the linear or in the fully connected layer, the parameters W and B were doing a linear transformation. Whatever was the input X, it was saying, hey, WX plus B, right? So here, the parameters corresponding to each filter, because there's a collection of filters now, parameters corresponding to each filter, they also correspond to basically a linear transformation. Okay, so it's just a linear transformation, and we'll see this transformation. So it's basically, let's focus on this. It's a linear transformation. Okay, and each filter outputs a scalar value, a single number. Okay, and we'll see how we get the whole tensor, because although we have a set of filters, if each filter is just producing one number, then the maximum number of numbers we can get is the number of filters, right? But no, I mean, we'll get the whole tensor, but we'll see how we get the whole tensor from just these filters or filter parameters. Okay? And just like in the fully connected case or in the feed-forward neural network, W comma B were getting learned, right, using backdrop. Similarly, these filter parameters, whatever the number they are, let's say the set is, let's say 10. So all these 10, filter parameters, 10 set of 10, I guess 10 times whatever the number of parameters are there in each filter, they'll all get learned again using backpropagation. Okay, that's the same, learning is the same idea. Okay, now here's an example of a filter. Okay, when I said a filter and it's a linear transformation, so we were talking about last time this CIFAR 10 data set. So the input had actually 3 depths because it's color image, and a width of 32 and a height of 32. Okay, so the height was 32, width was 32, and let's say depth was 3. Okay, so if my first layer happens to be a con layer, then I'm just giving an example of a filter. Okay, when I said, we just said, hey, if it's a con layer, the parameters just are just bucketed into filters. So let's pick one filter out of whatever the number there are. So one filter may have a, one filter can be represented using a tensor. Okay, so because it's a bunch of parameters, and so I can arrange them into a tensor. So just think of this as a tensor, which is 3 times 3 times 3. Okay, so 3 cross 3 cross 3. There's a box. So what do I mean by this filter? Although I'm drawing the box, just think of this as a bunch of 3 cross 3 matrices, 1, 2, and 3. So this is 3 cross 3, this is 3 cross 3, this is 3 cross 3, this is slice 1, slice 2, and slice 3. If you just stack them one below the other, these numbers, you basically get this shape, right? Right? And each slice will have whatever numbers, like -1, 0, 2, 3, 1, 5, 10, 0, 1, whatever the numbers are. And we'll see one example, very, very, very quickly. Okay. So this is an example of what you should think of as a filter. It's a bunch of numbers, but again arranged as a tensor, as a cuboid, okay, in this example. And because it's, as I said, if it's a first layer filter, then you can also say, hey, it has 3 pixels width and 3 pixels height, and let's say it also has 3 as the filter depth, okay, for 3 color channels. And you may say, hey, why are you talking about pixels here? We'll see in a minute why we want to say pixels when it's the first layer. Okay, but in general, this extra, let's not worry about pixels and all that. It has 3 width and 3 height, and 3 it's the filter depth. Okay, because it's 3 cross 3 cross 3. If it is 3 cross 3 cross, if let's say 3 times, let's say 4 times 3, then one of these numbers will be 4. And these sizes will also be something that we get to choose, okay? And we'll talk about it in a second. So is the notion clear that, hey, we have a bunch of parameters in Conv layer. Let's think of them in terms of thinking as sets of parameters, and each set of this collection of parameters, we're just gonna mold them into basically a tensor, okay, like a 3 cross 3 cross 3 or 3 cross 4 cross 3 tensor or cuboid. Now we have to say, hey, we have these parameters, we have the input, which we are saying, hey, is a tensor. For example, at the very beginning, we have an input, which is a tensor, right? It's a 32 cross 30 cross 3 color channels, 32 width and 32 height. So it's a tensor. So we have an input tensor. Now we have a filter, which is also a tensor. How am I gonna multiply these two, or not multiply, but how am I gonna use these two to get some output? Okay. So and we're gonna look at and the key idea is, we are going to convolve this filter with the input across the width and height dimension. Okay, so let me say the sentence first, and then we're going to really decipher what exactly it means. Okay, we slide or convolve this filter. The filter, we have several filters, so we can do, we can pick any one of them for now. We have to do this for all of the filters anyway. We slide the filter across the width and height dimension across the width and height of the input volume, and when we do that, when we do this convolve operation, we get a scalar output. Okay, so one single number, okay, which is passed through nonlinearity. So you can imagine right here that what I'm trying to say is that you have some input. If I use the filter, if I use the filter and this input, I can get one number. Okay, but if I slide okay, maybe I should go to the next slide and talk about this. It's the same sentence from before. Okay, so what do I mean by this operating with the input tensor? Okay, so for simplicity, let's actually drop make the tensor simple. Okay, which means that let's remove the depth. Okay, because if there was a depth of 1, it's basically a matrix, right? So think of it where there are no multiple layers in the depth. Can you hear me, by the way?
Yes, we can hear you.
Yeah. But, it said the connection is unstable or something. That's why I was concerned. So what I'm trying to say is that let's now, for this slide, let's squish the depth to 1, okay, where we basically think it's as an input, and therefore the filter will not, filter will also not have a depth, okay. And what I mean by this convolve operation, okay, convolve operation just means so let's say we have a filter which is of size 3 cross 3, and at the depth, let's shrink everything. Let's say the depth is it's a special case where depth is 1. Let's say the filter size is this. Okay. Now, what will be the input? Input will also have a same property. It will have a constraint that input is whatever size it is. For example, in this diagram here, it's actually 5 cross 5 cross 1. Okay. The input is 5 cross 5 cross 1. Since it's 1, so this one and this one are actually related. Okay. Filter depth should be the same as input tensor depth. And since it's 1, let's drop this, because if you drop it, it's basically a 3 cross 3 matrix and a 5 cross 5 matrix. Okay. Now let's see what convolve operation means. Okay. So we have the input, which has now become a matrix because I deleted the depth, and similarly filter became a matrix because I deleted the depth. Okay. It's a special case. Now, what does convolve mean? It's just element-wise multiplication. That's all what that's all it means. So as an example, you can see the top right in this diagram here. There's an orange color region. Okay, so I have selected a 3x3 piece of this 5x5 matrix. Okay, in the top left side. Okay, the numbers which are the big center numbers are the entries in the input tensor. Okay, so the 1 1 1 0 1 1 and 0 0 1 in this orange region are the numbers in the input tensor. Are numbers in the part of the input tensor. Okay, the part that we have highlighted as in orange, and the filter itself is corresponding is shown by the numbers which are in red. Okay, 1 0 1 0 1 0 and 1 0 1. Okay, so those are the two matrices, and so convolve just means multiply numbers element wise. Okay, so 1 is multiplied with the red number 1. The second entry here is multiplied by the red number 0. The third entry is multiplied by the red number 1, and so on. You multiply all of them, okay, and then you sum the total. Okay, you just sum the total, and total turns out to be 4, and that you save as the first number of your I guess convolution operation. Okay, with this filter. Okay, now you can see that the output has a 3x3 dimension for some reason, and the reason is as follows. What we're going to do is pick those red numbers, which are the top left, and just move them by one column, to the right. Okay. So what do I mean? So let's say the original 5x5 matrix. I'm not going to fill in all the numbers because that's 1, 2, 3, yeah. What we're going to do is now focus on this part. Okay. Focus on this part of the input. Okay. So the red numbers are just shifted by 1 to the right. Okay. So if we do that, then the numbers in this part are the data has 1 1 0, 1 1 1, and 0 1 1. Right. I just basically it's like saying, hey, let's focus on the numbers in the center. Okay, but again 3x3 only. And we have these numbers. Again, let's multiply with the red numbers. And what does it give us? So I see that we have 1 from the first top row. We have 1 from the second row. And we have 1 from the third row. And so add those 3 up, you get a number 3. So what do we do here? This, is the operation clear? So we just shifted to the right, and we did again element-wise multiplication of our red numbers with the shift. Once we shifted, once the orange region came to the center, then there's a different bunch of data in the input image or input. I wouldn't say image, but whatever, input image or input tensor, which just happens to be a flat tensor, so it doesn't have any depth. And so we got the second number. Similarly, we can get the third number when we multiply with something like this side. Okay, so from here, this 3x3 cell. Okay, and there is some number. I don't want to compute it, but some number here. Similarly, you can compute all these numbers. Okay, and you can see that, hey, once I slid to the third side and computed this number, I can't slide the orange region more because that will not give me a 3x3 matrix anymore. So what I'll do is again go to the left and go one row below, and then I'll have a 3x3 region here, and that will lead to this number. And similarly, once I have that, I'll again shift to one left, one step to the right, and I'll have this number. And similarly, one more step to the right, I'll have this number. So that's the convolution operation. This number here, you can think of this as the output of one neuron. Okay. Remember, we only have these, the red numbers are the parameters under consideration right now. So these parameters gave me a number, which is like a neuron output. Okay, after, let's say, some nonlinearity, but let's not worry about nonlinearity right now. But the same set of parameters also gave me the output of the second neuron, okay, which is on the to the right of it. Similarly, the same parameters were used to produce the output of the third neuron, which is the third number here. And they're just represented in, so all these numbers are produced by the same parameters. Okay, it's the same parameters, but looking at different parts of the data, okay, overlapping parts of the data. So that's what a sliding operation means. So only on the face, only on the width and height dimension, you are using the filter and sliding across the face of your input tensor, okay, and multiplying, element wise, and then adding the numbers together and outputting something. Okay. Now, I want to first show you the link below first, and then we'll talk about, hey, what happens when there's depth. Okay, and depth it's straightforward. So let's again reinforce our ideas using the animation from that link. So,
Professor, before you go to the link, I have a question. So I understood that we are taking 3 of the and doing the element-wise multiplication. So in this, where do we get this 101? The one we are multiplying with, is it other filter or any row picking from the same element?
So the red numbers, 1, 0, 1, 0, 1, 0, and 1, 0, 1 that you see in the, that that you see in the orange area, the red numbers, those are the parameters of the filter, or parameters, therefore they are the filter. Okay, they define the filter. Okay. And these parameters will be learned using backpropagation. Okay. So it's very similar to how you learn W comma B in the case. It just happens that we just picked 1, 0, 1. Generally, these parameters are not going to be like integers at all. But for this illustration, we just did that. And what's the, so now let's go back. Good, great question. So now let's talk about this link here. So new share. I need to look at what does the it not work? Oh, okay. Not, I didn't want to do Google search there, but yeah. So now what I want to show is that what is the effect of, like, we were in the example, we squished in the input. So generally, if you have an input which is a grayscale image, then it will only have one layer, right? It will not have colors. So there's no 3 depth for that input image. It's just going to be a matrix. Okay. So here you can see what is the impact of different filters. So here actually this page is trying to show what happens when you do this multiplication. So here you can see this red. I think, can you guys see on the yeah, actually, yeah, let me keep it here. So the first thing that you see here is some sort of a matrix. Okay, this is exactly like the filter weights. Okay, or the filter parameters, the 3 numbers, the red numbers that we were seeing in the previous picture. So there are a few options. You can change these options, but they all do different things. Okay, let's pick something. So let's say if these were the numbers, okay, here they're handcrafted, but let's say these were the numbers. And if you had a grayscale input image, it's a tensor, but it doesn't have depth. Okay, depth is 1. So clearly the filter also has depth 1. That's why I said the depth of the filter has to be the same as the depth of the input. And here the input is the image, because we are thinking of the first layer in this in the neural network. So it interacts with the image. So you can see what the operation led to. So you can see the figure on the left of this person, sure, it's pixelized, the figure on the left, and what happened to the figure on the right. Okay, that's the output of this filter. Okay. It turns out, I mean, it seems to be the same shape, but don't worry about the same shape here, whether the output is the same shape as the input, in the sense of like, it seems to be the same size as the input, but that's not important right now. What I'm trying to say is that because the numbers are, whatever these numbers are, -1, -1, -1, -1, 8, -1, and so on, you can see that it has picked up the outlines. Okay, so and that's why it's called the outline kernel or outline filter here. Okay, you can see that it has found the outlines of this input image, like where does the hairs, where does the transition between the skin and the hair happen, for example, right? Or you can pick other filters, blur filter, it kind of removes smoothens the the original image has pixelized representation. For example, eyes have now become blurry, so that's why it's called a blur filter. Okay, so this is what the filter is doing. Okay, here the filters have been hand encoded. So filters as in the filter weights, the filter parameters, right? Are hand coded. Identity doesn't do anything, but let's say we were talking about sharpen, some numbers here. These are hand chosen. Okay. But what will happen in neural networks is that same idea, same sort of idea, with of course some depth also, because you're going to work with color images, and therefore, and also if you use a conv layer at some intermediate point in your model, then the input tensor need not even be an image, right? It will not even look like this. The input is some tensor, and but the weights of the filter will be data driven, in the sense that they are chosen such that you minimize the cross entropy loss, for example. Okay. So so here you can verify that what this filter is doing. It's literally doing exactly the computation that we're talking about. So in fact, the computation is shown in the center part here, right? If I pick some region, you can see the number in each of the grayscale in that region is 185 times 0 plus 187 times -1 plus 182 times 0, and so on. Okay. So I hope this gives you a sense of like what is the filter trying to do, and there's some interpretation for certain types of filters. Certain numbers choose, will sharpen the image, or pick an outline, or or emboss the image, and so on. Okay, there are different filters, but these are hand engineered. Okay, but we'll see that in deep learning we don't have to do that. We just have to pick the size of the filter, and that will determine the output size. Here, it turns out that if you use a 3x3 filter, and you also do some extra work, like you can see that at the top, I'm only having 6 numbers instead of like the full 9 numbers, then you can get the exact same size input, exact same size output. But we'll talk about it in a minute. So let me, yeah.
Are there any methods used to choose matrices like this?
So these are hand engineered. So this is like hand engineered feature extraction stuff for images, you can say, which is quite popular, up to 2011, for example. 2011 ImageNet competition, or 2011 ImageNet competition was won by an SVM. Okay, so SVM that you probably, most of you have seen in 572. Okay, but it's SVM, but behind SVM, the feature engineering part involves decades of ideas about, hey, how do we think about images? What would be right features in images, right? So image is your only input. So you have to think of, hey, maybe these boundaries, if they're curving like this, maybe it's the face of a human versus, maybe an inanimate object. There's some intuition-driven designing of features. So this is just a collection of filters. And there are many filters that you'll see in many, I would say, even paint-related programs like Adobe Photoshop or GIMP or any of these. You'll see filters like this. But for deep learning, you'll generally don't use these. Okay, you'll just do it in a data-driven way.
Okay, that's good. Thank you, Professor.
Go back to between.
Hi, Teja. I think this might have been answered already, but how do you get the numbers that each number in the square is multiplied by the, for example, like the red numbers that you see in the picture right there?
Yeah. So the red numbers are learned using data. So those red numbers, just think of those red numbers exactly the way that you would learn, just like you learned W and B in your assignments, and therefore also in previous sessions, right? We were learning the W matrix and the B matrix. These red numbers also are basically something like W and B. Okay? They need to be learned using gradient descent.
Got basically.
It. Yeah. And they are exactly so in this layer, these are the only parameters. And so you have to tune these parameters so that the overall model actually predicts the right class. Let's say dog versus cat, it picks a dog to be dog and it picks a cat to be cat, right? But for a fully connected layer, it's clear what the parameters are. It's exactly the huge W matrix if it's too many hidden units, and some B vector. Okay, so those are the ones that need to be tuned. So now you have all these. Hey, for this layer, there's some filter parameters to be tuned. For this other layer, there's this W matrix and B thing to be tuned. And so for different, if you mix and match different layers, you'll have a bunch of these different. Each layer will have its own parameters, and you have to tune all of them together to eventually do well in classification or something like that. Okay, so let's move forward, and we'll actually come back to a 3-dimension. I would say something with depth in a second. An example with depth in a second. Um, um, but some things let's notice first. First thing is that filters are generally small. That, for example, small along width and height. Okay, so for example, we just say 3 cross, and this is not uh, an arbitrary choice, 3 cross 3 cross 3, let's say. Whereas the input image, let's say CIFAR 10 has 32 cross 32 cross 3, 3 for the red, blue, green. Okay, so if you choose a filter size 3 cross 3 cross 3, this is generally what people do in reality. Okay, people, researchers or deep learning folks, they generally choose small numbers for the width and height side of the filter. If you think of filter as a tensor. And filter depth itself, this number should be the same as whatever is the input tensor. Okay, so if the input is really the input image, then input image has exactly depth 3. So you have to better make the filter exactly depth 3. But if the con layer is somewhere, is like the 5th layer, okay, so which means that maybe there are 4 layers before, and therefore there were 4 tensors before. And so by the time you have an input to the 5th layer, that tensor may not have a depth of 3. It could have whatever depth. Okay, it could have a depth of 10, for example. Okay. And I'll show you how you can have a depth of 10, for example. If it has input has a different depth, let's say a depth of 10, then the filter should also have the same depth, okay, depth of 10. Okay, so the filter thing is determined by whatever is the input depth. Okay. As we slide this filter, okay, onto the across the input, what we get is called a 2D activation map. Okay. So it's basically a matrix, and you saw that this is basically a matrix. So for one filter, we get a matrix. Okay, as we slide it across the input. Now you can imagine if I had 10 filters, I would get 10 matrices. Okay. If I had 10 filters defining this con layer, remember that I said con layer is defined by a set of filters. So let's say my set of filters is my set size is 10, which means that I have filter 1, filter 2, filter 3, filter 4, filter 5, filter 10. Okay. So if I use filter 1, I'll get a matrix like this. If I use filter 2, I'll get another matrix. Similarly, all the way, if I use filter 10, I'll get another matrix. Okay, so now I have 10 matrices. Okay, each matrix is called a 2D activation map, and you stack all of them together, and you get the output tensor. Okay, which means that each slice, so each of this 2D activation map, there's a bunch of numbers in each of the 2D activation maps, right? Like this number 4 here, this number 4 here. You can think of that number as the output of a neuron, but the neuron's parameters are the filter parameters. Okay, so for example, this you can think of this as a neuron whose parameters are those red numbers. Okay, 1, 0, 1, 0, 1, 0, and so on. Okay, similarly, the second neuron also has the same parameters. Okay, because literally we use the same filter to produce the second number 3, right? And similarly, the third number we also have the same parameters here. Okay, so each of the 2D activation maps, okay, will have a bunch of neuronal outputs, but all the neurons, you can just conceptually, all those neurons have the same parameters or the same weights. Okay? So everything in the 2D activation map corresponds to, each 2D activation map corresponds to one filter, and therefore all the outputs there, even if you conceptually want to think of different multiple neurons, they all have the same parameters, so exactly the filter parameters.
So, Professor, totally there'll be 3 into 3 neurons in that particular layer.
Yes,
Is it?
yes. Yeah. So you ignore the depth, whatever is the so this size, output size is just determined by how much sliding flexibility I have. For example, if my input had, instead of 5 cross 5, it had like 7 cross 7, my output would be a little bit bigger, right? Because I can slide a little bit more. Yeah. But it's whatever. So the number of neurons, exactly. So the 2D activation size, the 2D activation map size in terms of width and height, it's just determined by, it's not predetermined, but yeah. But all those neurons will have the same parameter. You think of it's driven by the same parameter, which is the filter weights or filters parameters.
Okay, so you gave an example where we had 7 cross 5 as as the input. So how many neurons will be there for that?
So we'll see an example in 1 second. So let's talk about, hey, how does the output size, as in the 2D activation map size, So let's hold on that thought for a second, and we'll do another example and we'll talk about it.
Okay, and I have another question. How is this better than the one that we used to do before, like
Yes.
the hidden layers and all that?
Yes,
Like
yes, yes. And we'll do a parameter counting exercise in a second to talk about we reduce some parameters. Okay.
Okay.
There's going to be some benefit on parameter side, and there's also some benefit because we're working with images. Okay. So this conv layer is trying to take advantage of something about images. Okay. And we'll talk about that intuition in a second. So that's both are great questions.
Thank you. Professor,
and how is it better than fully connected?
I think so. You forgot to post the annotated notes previously, like the previous class.
It's linked there. So it links the whole notebook, right? So if you go to a syllabus page and go to textbook material section, there's slides and there's an extra annotated slides link. Okay, it's actually a OneNote notebook. Okay.
Oh.
If you have the UIC UIC email access, then you can see the slides, right?
Okay, Professor. I'll check it out during the break if at all. If I don't like know how to do it, I'll ask you again.
Yeah.
Thank you.
It is working with all of the annotated notes.
Oh, okay. All right. Okay. Thank you, Matt.
Yep.
Yeah. So I guess this slide is same as before, but what I'm this slide is just making a minor point, basically that these parameters are learned the same way as you would learn the weights of a regular fully connected neural network. Okay, but the point is they will learn in the ways in terms of intuition. They'll try to detect some features. Okay, at least for the if you think of filters that are interacting directly with the input image, okay, they'll exactly do the type of things that we saw in that animation, that link. Okay, that Setosa link, where they'll try to find edges in the image or try to find outlines or some curves in the image, or even sometimes colors in the image. Okay, so because all this information can probably help you classify something as A or B, right? For example, grass is typically green, or so green color may be indicative of, hey, this is grass and not a road, or for example, a road is generally gray or something. Okay, so colors are also useful. So anyway, these filters are supposed to detect certain visual features, and then this is the same idea that was there even before, right? Before even before talking about neural networks and convolutional neural networks, folks were using HVMs. Okay, but when they were doing feature engineering, they would have a color based feature coordinate, and maybe how the edges are there, how much curvature is there between edges, how much is the distance between maybe eyes that you detect, and so on. So there is a lot of things that folks used to do. Okay, but the filters are supposed to detect some patterns. Okay, and filters at the extreme beginning, which means that if they're directly taking the input tensor is just the image itself, it's very easy to kind of intuit about what could filters do. They would just detect obvious things like colors or edges and so on. But if you think of a conv layer appearing in the, let's say, the fifth is the fifth layer in a neural network architecture, okay, then it's not exactly clear what they're detecting, but we'll see we'll see in a maybe not in the first half, in the second half we'll see maybe they're still detecting some higher level features. Okay, for example, a dog versus a cat, they have some overlapping features, but there are also some distinctive features. Okay, so filters at higher levels, in the sense later on in the network, may detect hopefully some higher level patterns of, hey, this looks like a cat or this looks like a dog. But we'll see in the second half about that interpretation. So yeah, this is probably second half or the next lecture or the next module. Second half. Okay. But let's look at the neurons themselves, and I've already kind of gave you the teaser of what the neurons were. But let's recap that right now. So we'll discuss, hey, how are neurons connected, how are they arranged, and how we get reduced parameters. And this hopefully answers one of the questions that you raised. And so let's talk about these three questions. Okay, so each neuron you can think of, it's getting a as input a local snapshot of the input. Okay, so that you can already see, right? So if you think of this number 4 as the output of a neuron, this guy is only seeing the top left of the input, okay, the orange region only of the input. So like neurons are generally getting only partial local regions of the input as, of the full input tensor as their input. Okay, so they're only seeing like a part of the input of the input tensor. So this is called the receptive field of the neurons, or basically, it's basically characterized by the filter. And so here's a figure. Okay, so what is this figure showing? So let's say we are at almost the beginning. So let's think of this input as the image itself, the CIFAR10 image. It's 32 cross 30 cross 3. Now, if you think of the output tensor, okay, so let's say I said I have set of filters, right? Let's say my set of filters is, the number of filters is 5. So filter 1, filter 5, filter 1, filter 2, filter 3, and filter 4. Okay, so we have 5 filters. And this output tensor, you can think of, hey, let me put my 2D activation maps, okay, next to each other. Okay, so you can think of this slice here corresponding to one activation, so corresponding to one filter. So this is like for, let's say, filter 5. This is for filter 4. This is for filter 3, for filter 2, and this is for filter 1. Okay. So let's focus on filter 1 now. Okay, so what have I said so far? Each filter will just produce a 2D, it basically produces a matrix. Okay, so I just stack these 5, because I have 5 filters, I have 5 matrices, I stack one after the other. That gives me the depth. Okay, because I have 5 filters, now the output tensor depth is 5. Okay, important point to note. Now let's focus on the first filter. Okay. The first filter, let's pick some arbitrary cell. It's a matrix, so just pick one ij coordinate, some number. That's, as I said, that corresponds to neuron. Now that neuron, and we just talked about this, is basically looking at only a small part of the input. Okay, so it's only looking at, let's say, the center part of the input. Okay. And this becomes even clearer, right? So let's say if you want to detect a cat, or so detect whether, okay, so detect a cat versus a human, let's say, then you can detect whether the maybe this filter is trying to see whether, trying to detect whether the cat ear patterns appear or not. Okay. And so you can say, hey, this neuron should fire if there's a cat ear pattern in this spot. Okay. But cat ear pattern may not be in that spot, right? It can be in the top left, top right, anywhere, right? So the same filter is being applied everywhere, so that it doesn't matter where the cat is, or therefore the cat ears are. At least this filter can figure out, hey, this cat ears, and therefore maybe most likely there's going to be a cat. Okay, so that's the intuition. So there's some local aspect that's being captured, so spatial invariance that's being captured by these filters, by using these filters. So this filter 1, is produced a lot of numbers here, and the number of parameters, let's say it's a 3 cross 3 filter, because the input depth is 3, the output depth is 3, but the other 2 choices where we just made some choice. Okay, then the total number of parameters is just 28. Okay, there's the filter weights themselves, and there's also a bias parameter. I think I did not explicitly say there was a bias parameter, but you can just say, even in this figure, sorry, let's say there's a bias parameter plus 0. Okay, so you multiply with those numbers, but you add something. Okay, so I just added 0, so it doesn't matter. But you can say, there could be one constant number that you add to every entry here. Okay, for every cell here. Okay, so sorry, I'm making a mess here, but let's call it a bias parameter. Let's say it's 0 for now. So the total number of parameters you can have for filter 1 is 28. Similarly, number of parameters for filter 2 is 28, and filter 3 is 28, and so on. Okay. So let's come back to this point about 28. So right now we have 28 times 5. If we have 5 filters, so these are the number of parameters which completely determine the output tensor. Okay. And input has 32 times three bunch of numbers. So this was some huge number, right? Yeah, 3096 or something. 3072 or 3096 or something. Yeah, so there's some, these are the number of, if you think of input as a vector, these are the number of coordinates it has. But it's not a vector, it's a tensor, but these are the number of numbers you have. And the number of parameters that you're using are actually, you can see already here, it's not too many, right? It's 140. Yeah, number of parameters you're using to use, to get multiplied with this input, any input image is only 140. Okay. Whereas if you had a fully connected layer, you need, for each neuron, you would need 3072 parameters, right? So whereas with just 140 parameters, we have produced a huge output tensor. I'm not telling you the width and height right now because I'll tell you the width and height in a minute. But the number of parameters is much lesser than even for one neuron you need these many parameters, but for all neurons, total number of parameters have used is only 140. Yeah, so here I just wanted to show that, hey, if you think of the filter one's neuron, let's say this neuron here, it's looking at this region. Filter fifth, let's say fifth, filter five's neuron, the last activation maps neuron, let's say in the same, depth, in the same coordinate here, is also looking at the same region. Okay, so these 5 neurons are looking at the same patch of input here. Okay, but each of these, of course, 5 neurons correspond to each of the 5 different filters that we have. Where we arrange the filters like this, right? Remember? Yeah. So any questions about this part before I further explain a few more terms?
So the professor, in the example that you gave, like detecting a cat and a human. So you said that the filter will be trying to find if the picture has a cat feature, which is like the ear that you mentioned. So all the filters do the same job of detecting whether the image has the cat ears. Is it?
No. So filter. So I just gave an intuition of what could the filter weights be. So we haven't. So filter weights are first, need to be learned in a data-driven way. So filter weights are just like the linear layers, W, B parameters that you've been doing in assignment 1, for example. They need to be figured out what's the best choices so that you minimize cross-interval loss. Okay, but you can interpret, and we'll see actually a diagram where you can see the filters and say, hey, these filters are actually detecting color, or these filters are actually detecting edges, and so on. So the lower-level filters really don't detect ears. Low level in the sense that the filters which are, if the con layer is right next to the input image, in the sense that the input is directly fed to a con layer, which is the first layer in a multi-layer network, then they just don't detect ears themselves, but they'll detect some edges and stuff like that. Okay. But them detecting edges was in a data-driven way. So we didn't hard code it as the way we didn't hard code, or we didn't feature engineer to say, hey, this filter should detect edges, or this other filter should detect something else, and so on.
So usually the layers, like how will the layers be designed for? Like you mentioned that the con layer won't be present in as a first layer. So
no, it can be first layer. I'm just saying. So you could have, I think we saw. So we could have a con layer. So so generally I don't want to draw all sorts of tensors now, but you can say con layer and then a fully connected layer, then a con layer, then a fully connected layer, then fully connected layer, and then scores. And in fact, that animation link that I gave in the chat, I think there were 2 con layers followed by 2 fully connected layers, I think. We'll come back to that diagram, okay? And then we can talk about these layers. Okay? So I think they had 2 or 3 con layers and then 2 fully connected layers.
Okay, got it.
Yeah, you can look at, I don't want to switch now because it's a little bit of a task to switch back from here to there, to the browser, but we'll actually go back to that diagram and then we'll look at layers.
Sure, Professor. And it's also data-driven, right?
Yeah, I mean, all the parameters in the model have to be data-driven, right? So they cannot be hard-coded. So parameters include the fully connected layers, W, B parameters, and the con layers filter parameters. If there are 5 filters, each filter will have its bunch of parameters. They all have to be figured out in a data-driven way using basically gradient descent. Yeah.
What about the sequence of the layers that we are using, like the CFC?
Those are, some things are design choices. So you, like for example, what I wrote here, you get to choose, what layers, and you also get to, so you get to choose a few things, okay, which is size of the filter, for example, okay, which is instead of 3 cross 3 cross 3, let's say if you're at the entry, I said the depth has to be, has to be 3 because the input has 3 as a depth, but instead of 3 cross 3 cross 3, you could have had 5 cross 5 cross 3. And in fact, one of the original architectures from 2012, which actually made a splash in the ImageNet competition, it had 11 cross 11 cross 3 filter size, okay, which in the first con layer is very different, right? I mean, but these choices, by the way, I mean, looks like the community has converged to small filter sizes, and that was one of the point I just mentioned earlier. So folks are now using 3 cross 3 filters mostly.
Okay.
But the first version had like not first version, but the one of the architectures had 11 cross 11 filter.
Okay. Thank you.
So there's some choices I make, and I'll tell you what choices you need to make.
Okay. Got it.
This section. Okay, so now let's go back to the. So we saw what the neuron is in this con layer, and let's come back to the layer view. Okay, so as I said, the output tensor depends on 3 things. Okay, and that's where what I left out was what's the width and height of the output tensor. I said the depth has to be determined by, if you take 5 filters, the depth of the output tensor will be 5. If you have 10 filters, the depth of the output output tensor will be 10, right? So this part is clear. Okay, the output tensor depth is just the number of filters I pick, and that's where if it has depth 3, but in the first con layer I already picked, let's say, 10 filters, then the output tensor will have depth 10. Okay, and now the next time if I want to use con, filter will have to have depth 10. Okay, so there's some quick point I wanted to make. Now the width and height of this output tensor are captured by how do we slide in the spatial dimension. How do we slide this filter onto the input tensor? Okay, and that's characterized by 2 parameters: a stride and zero padding. Stride just means how much is the filter moving. Okay, is the filter moving 1 column at a time or 1 row at a time? Remember in the previous example we said 1 time and 1 row at a time, and that's why we got a 3 matrix there. Okay, and that's what is called a stride. Okay, and zero padding means, hey, are we, so whatever the input tensor, are we adding some extra rows and columns on the boundary in all of the whichever, how many our boundaries are there? Are we adding extra rows and columns? And zero just means we are going to put value zeros in those locations anyway. If we add some padding, okay, before we slide the filter, then that's also going to impact how big is the output tensor, right? So if I don't add extra rows and columns, certainly I'll have some range with how much I can slide. But if I can slide a little bit, right? So that's going to change how big I get. Okay, and certainly the filter size, 3 cross 3 versus 11 cross 11 or something like that, that's also influences how big of an output tensor I get.
Could you please explain the zero padding again, Professor?
Yeah, we'll actually see zero padding right now. So great question about zero padding. So let's come back to the picture we had. So this is an example of stride is equal to 1 and zero padding is equal to 0. And I'll show you. So now zero padding just means, hey, what if I added zeros here? Okay. And if I have a depth, I mean, I'll just add zeros for every matrix in that input tensor. So first of all, we only have tensors of dimension 3 mostly here. So this is basically a zero padded. We had an original input. We did some little bit of free processing before we slide with our filter. Okay, so that means the output here is it turns out that the output is going to be, if we add zero padding like this, then the output is going to be the same size as the original input. If you don't do zero padding, if you do stride 1, no zero padding, you know exactly what the output size is. It's 3 cross 3. Okay, this was a 5 cross 5. Depth, let's not worry about the depth. It's 5 cross 5. You got 3 cross 3 here. Okay. It basically will, because we had a 3 cross 3 filter. Okay, that's fixed. we get a 3x3 output. But if you have a 3x3 filter, but we add zero padding, and therefore because we added zero padding, it became 7x7, right? Because we have the number of rows to be 7, number of columns to be 7, right? Now, if we again slide 3x3 filter, we'll be able to slide a little bit more, right? So we'll be able to take the top. Sorry, not in this figure. This is the output figure. So let's say this 4 number here will be corresponding to this. Okay. So these numbers here, these 3x3 numbers will be exactly the center parts here. Sorry for the little bit messy diagram here. But because we had extra zeros, you can imagine that the orange region can now go one step left and one step top as well, right? And if you do one step left and one step top, and if you think of data as being zeros here, sorry, let's put a 0 there. So if I go one step left and top, then I have extra zeros, but that's the data. So this, what I'm talking about is this region, right? The one in the dark red area. Now, if I multiply the red numbers in the dark red area, you can, I don't know if you can eyeball. I think we get 2.
Top left first.
Yeah, we get 2 here or something.
Yeah.
Okay. So so how did you get 2? Basically, it's you can see. I don't want to. Yeah, let's do it anyway. 0 0 0 0 1 1 0 0 1, and this is the data. And I'm saying, well, let's multiply with 1 0 1 0 1 0 and 1 0 1, right? So you can see only this guy and this guy remain, right? And you add them up, and that's 2 here. Is this clear? So zero padding is just adding extra stuff to the original input, so that maybe you can get a slightly different size output. Okay. So if you do zero padding equal to 1 here, then what I'm saying is, if your input was 5x5, your output is also going to be 5x5. Whatever your input size is, if it's 10x10, if you add 1 extra zero padding, and if you have a 3x3 filter and stride is equal to 1, then you get the same size output. Okay.
The output has changed, and like whatever we
I mean, the output is, so the whatever we were getting before without zero padding, that would be in the center part, right? These numbers are the same.
Yeah, that is what we are looking for, right, Professor? Why do we need that zero padding?
That's a great question. So why do we do zero padding? And you can, okay, at this point, let me go back to that other, to the browser. So you can see here, right? These guys are actually doing zero padding in this animation. Okay, so you can see if I go up, you can see that I'm only looking at 2 rows here, right? So like let's go to top. Sorry, top. Yeah. So top, top left, I only have the red. If you look at the red area, right?
Yeah.
It's only looking at the 4 original image pixels.
Yes.
And you can see question marks in the actual multiplication that's going on. The question mark, just think of it as actually zeros.
Oh, okay.
Okay.
And it creates a border, or like we don't lose.
It's just producing, actually it's producing question mark as the output, so which actually is 0. It should ideally produce these extra numbers, but it's not doing it here. But what I'm saying is, why do we care about going, why do we add zero zeros on the border, first of all, right? It looks like we are distorting the input, right? The original input did not have zeros, now we have added zeros. That's, one, I guess, heuristic reason is basically that you want to capture some patterns which are at the edges.
At the edges.
Okay? And you can imagine, right? Yeah.
Yeah, and also is it because that we should not lose the like the data which is present at the edge, or maybe like to make sure that we have captured everything? Is that the reason?
Yes, okay. Yes. But you can say, hey, why zeros? Why can't I put the median value of the image, median value of that pixels in that extra, in that boundary or something? Zeros is something that people have converged onto as an empirical choice. Okay.
Okay.
Because it doesn't mess up with some computation. Zeros, it's easy.
It's easy.
It has some computational advantages as well. Yeah.
Got it.
Yeah. But it's mostly about going to the corners and in boundaries. If there's some patterns, hopefully your filters can pick them up. Yeah.
Oh, okay. Got it. Thank you, Professor.
Now let's come back to that figure. Where is it? Yeah. Let's come back to this this picture here. Okay. So now you can see why they're only showing few of the edges, right? So you can see here they're only showing few edges, right? Or any of these places, there's only showing few edges, right? Actually, this should not be. Okay, so you guys can see when I scroll over, when I move my mouse, you can see some edges getting formed, right? Like this, you can see 4 sets of edges, like, you know. Yeah. Okay, so this is actually a deep neural network, an example deep neural network. So input image is this, okay, at the bottom. The first layer happens to be a convolution neural network layer. Okay, sorry. First layer happens to be a con layer. So you can see, hey, this pixel, or this. So you can see that this pixel, or that cell, happens to be only looking at the top left part of the input image. Okay. Now, how many filters are there? There are going to be, there's actually 1, 2, 3, 4, 5, 6 filters. Okay. So you can see that's because there are 6 different 2D activation maps. Okay, so you can, if you look at this row here, this has 6 2D activation maps, so 6 slices. Okay, so you put them on top of each other. That's output tensor after the first con layer. Okay, and you can see any pixel is only looking at a small region of the input. Okay, is that clear at least? This is actually an example of a con layer. This first layer. What we are seeing here are the 2D activation maps for this input. Okay, we're not seeing any filters. We're not seeing anything. We're just seeing, hey, whatever with the filters, it's all occlude. It's not shown to us. But given the filters, given this input image, these are the 6 2D activation maps that I'm getting. Okay. They are basically, if you stack them together, that's the output tensor that you're getting for this input image. Now, what this example is also doing is they are having one more con layer, but the animation is not working out well. So actually, this con layer should look at all the 6 inputs. Okay, so
Professor,
yeah.
I don't want to disagree with you, but I think I read the thing, and I think they're doing a pooling reduction layer between the convolution layers.
Okay, great point. Yeah, John, thanks. Got it. Okay, let's actually skip one more level here, and you can see it's actually connecting everything. Great, thanks, John. So yeah, let me talk about this thing. The smaller row here in a few minutes. Okay, but that's actually what it's doing is downsizing, pooling operation. Okay, so that's why it's only related to the previous. I would say, so pooling happens at each activation map by itself. Okay, so it doesn't depend on other activation maps when you're trying to downsample. It's basically trying to shrink the input. So this matrix has whatever size, let's say 64 cross 64 or 32 cross 32. Then this matrix here will be like 16 cross 16 or something, like some shrinking. Okay, and we're going to talk about that in a couple of minutes. So let's skip that. Thanks, John, for the correction. Let's say there was a pooling operation here. Let's not worry about this row here. Okay, the third row from the bottom. The fourth row from the bottom is actually, again, a con layer. Okay, so you can see that it's only looking at parts of the input. So it actually should have 2 extra, I would say, edges going to the leftmost input tensor, I guess, slice, and the rightmost input tensor slice, but it's only showing 4. But you can imagine like 2 more. So this is again a conv operation. Okay, it's basically only looking at parts and computing that element-wise multiplication, summing them up, summing them across the depth, and the output is being shown here. Okay, and so how many filters are there? You can just count the number of number of images here: 1, 2, 3. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14, it looks like 14, 14 filters are there. And then again, the next row is again a pooling layer, as John mentioned earlier. So it just shrinks this matrix. Okay, if let's say this is an 8 cross 8 matrix, it's becoming a 4 cross 4 matrix here. And we're going to talk about pooling in a second. So how this shrinkage happens. But once you get this is a tensor. Now it's a 14 cross, let's say 4 cross 4 tensor. Now what they're doing is going from this tensor to basically a tensor which is like which doesn't have any width and height. Okay, so it's basically a tensor with only like depth, or basically a vector. That's what we're getting to. And this, you can see that any cell here or any neuron here is touching everything in the previous layer. So it's basically a fully connected layer. Okay, so each neuron here will have its own parameters, which are taking as input everything from the input tensor. Okay? And similarly, this is a fully connected layer. This is very clear, right? Every neuron is connected to everything, every input from the previous, whatever previous tensor. Similarly, the final score is connected to everything from the previous tensor. So I hope this animation makes it a little bit clearer about at least the con layer. We'll talk about the pooling right after a break. If there are questions, let's take it now or maybe after the break.
I have a question. What's the point of that downsampling here? We see just
on the third row and as well as fifth row, right? So this downsampling is just to manage the complexity of the number of parameters. Okay. So it's just that you can drop the downsampling. That's fine. But turns out that if you downsample, then the later fully connected layers don't need to have too many weights. So if you for example, the fifth layer, if you don't downsample, the next fully connected layer will have like 4x the number of parameters each. 4x the number of parameters, for example.
Okay, thank you.
Yeah, but we'll talk about this downsampling or pooling business in a little bit more clear way through a smaller example right after the break. Okay. So look at this figure, and if you have questions, let's pick it up again right after the break. Okay. Let's take a break for. Actually, I want to see what time it is. Let's resume at 7:44. Okay, so let's resume. Any questions so far about the animation that we used, that we saw earlier, or the description of zero padding and stride and so on? Okay, if there are questions, just do put it on the chat, and I can try to answer them. I'm trying to figure out where the chat window is. Okay, got it. Okay, so I guess I showed the animation which had an element which we did not discuss yet, which is the pooling layer. But we'll get the pooling layer in a couple of minutes. Okay. So let's again, focus back on like what is the advantage of a con layer compared to a fully connected layer that I think Supriya asked earlier. So I think I mentioned it even at that time that the key idea is that, especially with images, not just at the first, not just when the filters are interacting with the image, but even at subsequent layers, potentially that if a filter is useful for one region of the input tensor, then it could possibly also be useful for another region of the input tensor. For example, maybe the filters at the which are closest to the input image may just detect some simple things like edges or curves or colors and so on. But maybe filters of a con layer, maybe which is like a fifth layer in a neural network, may detect higher order features, bigger features, like maybe the face, an outline of a face itself, or things like that. Okay, so that's a intuition for why filters may be useful, why filters and striding may be useful, because that's such a face can be probably not just be in the center of the image, but maybe at other parts of the image, right? So you have the spatial invariance property thanks to, because the filter is sliding through the spatial dimension of the input tensor. And this is what we just saw, that all neurons in each depth slice or each of the 2D activation map use the same parameters. These weight and bias parameters are the parameters of the filters. Okay, so once you're on the same slice, you are using the same parameters. And therefore the number of parameters is quite reduced. Okay, so for example, if the number of filters is m, so you just have these many number of parameters. And we saw if there are 10 filters, there's 280 number of parameters. And okay, and so you just need to update 280 number of parameters for a layer. Okay, and of course these parameters, you can call them filter weights and filter biases. So they actually, for all practical purposes, can also be just called, let's say you can also use a notation W, B. It's just that now these W, B are probably just going to be much smaller, right? So W is going to be a 3x3x3 tensor, and a B is just going to be a 1x1x1 tensor. Okay, and once you have this W, B, then you just do same idea, the gradient updates. Okay, gradient updates on this W, B. So here's the first example of a real-world neural network and how the con layer looked like. So this example is for LXNet, which is from 2012. And so this was the neural network, it's by Jack Hinton and a student, which basically did really well on the ImageNet large-scale visual recognition challenge. And the first layer was a con layer with filter size being 11 cross 11 cross 3. And 3 we know because the images were ImageNet images also have depth 3, okay, for the 3 color channels. And the number of filters they use in the network is 96. Okay, So 96 11x11x3 filters were used. And here, what we're showing is these filters, because they have size 11x11x3, and so you can actually think of them as images themselves. Because they have depth 3, you can think of, hey, I have 3 matrices, which are each of size 11x11, 11x11, 11x11 each. Then I can just think of that as an image by itself and just visualize that as an image. And that's what we're doing here. Okay. So you can see that these filters, if you think of visualize them as images, it seems like they are detecting edges or colors or combination of colors and so on, some checkered pattern and so on. Okay. I mean, the filters weights are like this, and you can imagine filter weights, for example, where their lighter is higher and when their darker is lower. When they multiply with an input region, they will pick up, if there is a signal, for example, here, they'll pick up that signal. Okay, so you can imagine like the filter weight light regions to be the patterns that the filters are trying to detect. Okay, so yeah, and again, the same intuition that if they're detecting certain edges are important, then the same edges should, it's important to detect it anywhere if it appears in the image. Okay, so so this is an example. This is an example visualization of what the filters look like. Of course, from then on, I think that, as I said, the recent state of the art or recent rule of thumb is to use smaller size filters, so 3x3 generally. Whatever is the depth, if the con layer is at the first layer, then the depth is 3. If the con layer is like the second or third or fourth layer, then the depth is going to be whatever is the input tensor's depth. Okay. And so here's an example. I will not spend too much time on this example, but I'm happy to. You guys should check out this link and also look at the slide. It's basically a screenshot from an animation from that link. So what this example is trying to do is to show you stride is equal to 1, 0 padding is equal to 1, and filter 1, so filter 0 and filter 1. Okay, there are 2 filters, so therefore there are 2 activation maps. Sorry, stride is equal to 2. Okay. Yeah. Okay, and there are 2 filter maps, and the filters are given by this. This is one filter. Okay, because the input depth is 3, so you can see there's this things in blue that were the original input tensor, which has size 3, so which has depth 3. It's 0 padded with the gray rows and columns. Okay, and because depth is 3, the filter should also have depth 3. Okay, and finally, this filter's output is, let's say, this green matrix, the top green matrix. And the second filter's output is the bottom green matrix. So if you look at this entry, the entry number, the first entry of the second filter, then that number was computed by doing this element-wise multiplication, not just on the first layer. Okay, you do not just on, so it's not like doing element-wise multiplication of the first guy with the first guy. You also need to do element-wise multiplication with the second guy and the second slice of the input, and the third slice of the filter, third slice of the input, and add them all together. Okay, and you also bias. Okay, after adding all of them, that number is equal to 1. Okay, that's all I want to say here. Think about it. It's a good example to see and also visualize from that URL of how the conv operation works. Okay. So are there any questions about conv layer? We've already discussed hopefully why zero padding, why parameter reduction, how parameter reduction, sorry. And what is it taking advantage of? It's basically taking advantage of the fact that images have spatial invariance structure, in the sense that images can have things at different locations, and looking at small regions and then somehow aggregating that information later on, maybe later on layers, is a good idea.
So, Professor, I have a question.
Mm-hmm.
So you explained it earlier. If you can just describe it one one more time. So you mentioned for 3x3x3x3, we have 28 in total parameters. So
yeah,
can you describe how we actually come up this number 28?
Yeah. So you can see that here, okay, let's focus on this guy, the second filter. Okay, this is the second filter, W1. I think they're just referring it by W1. So you can see there are 28 numbers, right? So there are 9 numbers in the first slice, 9 numbers in the second slice, there's 9 numbers in the third slice, and then 1 extra bias number. Okay, so there are 28 numbers here, right? 28 cells. The numbers inside the cells themselves are learned using gradient descent, right?
Oh, I see. So the numbers inside the cells, those are also parameter.
Yeah. So numbers inside the cells are the parameters. What you're doing, so there are a lot of choices to make, right? Some choices you are just hand picking them. The choices are, hey, what should be the size of the filter? Why is it 3x3x? Depth is depth. It's not something that you. So depth is, at least the input level, is going to be whatever is the input depth. But why 3x3? Why not 4x4? Why not 5x5? You choose. But once you choose a filter size, let's say the width and height dimension, the numbers inside them you have to choose just like how you do for a regular feed-forward network layer, right? You have to pick those numbers using gradient descent.
Yeah, I see, Professor. Thank you.
So in these examples, we're looking at integers, so it looks like we have handpicked them. It's not the case. Okay.
Yeah, I understand now. Thank you.
No problem. So any other question other than Nahid here? Yeah, I would suggest folks, if there's questions about this slide or earlier slides, do stay back and I can explain things again. In the interest of time, let's move forward to pooling layer and talk about it, because we just saw it in the animation and I made a mistake there. Thanks, John, for correcting it. So the pooling layer is a, we're just calling it a layer, but it's a very simple layer. In a sense, it's a very straightforward layer. And the objective is just to shrink. Shrink the input tensor. We just want to shrink the input tensor. And I think Suror earlier asked, why are you doing this? It's basically to, it's basically a trade-off, saying that, hey, if so if you shrink the input tensor, the subsequent computations are going to be lesser, because if there is a lesser number of numbers, then certainly the computation decreases downstream. But at the same time, we should not shrink the input tensor too much that we lose information. Okay, so empirically, people have found that, hey, pooling helps, especially when it tagged along with the convolution layer. Okay, so there's few, I guess, details. There are a couple of details about how do you shrink this input, and let's look at an example. Next. And as I said earlier, this shrinking only happens on the spatial dimension. Okay, so think of a tensor. It has some depth. Okay, we are not going to touch the depth. We are only going to touch the width and the height. Okay, we are just going to somehow shrink the width and height. Sorry. And so since we're not going to touch the depth, each depth slice or each 2D activation map that we're talking about, for each filter, there's one matrix, right? So the pooling operation happens independently in each of these for each filter's output, basically. Okay, so let's look at this example. So if we had a input tensor of size 224 cross 224 cross 64 here, so 64 is the input depth. Okay, and we just maintain the same depth. And here's one example of a pooling operation. We're going from 224 to half those numbers. Okay, 224 to 112. So the width and height got decreased by half. Okay, so you can also call it downsampling or pooling operation, basically. And so you do it per slice. So here we're saying, hey, pick a slice, downsample it, or pull it, and then put it back in to get your output tensor. Okay. And here's a pooling example of how exactly do you shrink the numbers. I think this should be also a little bit clear to you folks that the way to reduce the number of numbers is somehow take averages or maxes or mins or some sort of a summary statistic, right? So in this example, we have a 4x4 matrix, and we are shrinking it to a 2x2 matrix. And you can see that this number 6 is just some sort of a function of the top 4 numbers. Okay. So and similarly, the second number is a function of the next 4 numbers. Okay. So if you want to divide by 2, essentially on the spatial dimension, you generally want to group or look at, let's say, roughly 4, okay, 2 numbers on the in the width dimension, or in terms of the columns, and 2 numbers in terms of rows, or in terms of the height dimension. Okay. So here you can see that, hey, how did I get 8 or 6? You can see it's the maximum available in each of those groups. Okay. So there's one example of a pooling operation that you can do. You can certainly do other things. For example, you can take an average 5 plus 6 plus 1 plus 1 divided by 4, whatever the number is. You can take that as the output here. So that would be called average pooling. What this example is called max pool, as it says here. And they're also saying filters, but it just means that you're looking at 4 numbers at a time. Okay, and the same idea applies. You slide. If you're just taking a max, you have to take a max of the first top left, and then slide 2 steps to the right and take an average. Sorry, take a max, and again slide 2 steps to the right and take a max if it exists, and so on. Okay.
Professor,
so that's pool operation. Yeah.
So here I see that we are taking max of the first 4 cells in the first part. So what if 5 was an important character of the image that we might have wanted, or it's also one of the important character for 6 to be detected, maybe, I'm not sure. If we lose that information, don't you think we'll be losing a lot of lot of information from the image, and the output will differ, right, Professor? So
yeah. So
I know that
the first question is about loss of information, right?
Yes.
So yes, obviously, right? So there's lots of information. For example, lots of information can be easily said this way, right? So if I give you this matrix, you cannot construct this matrix, right?
Yes.
So clearly I cannot, so I lost 5 and I lost 1 and 1 as well.
Yes.
But it's a trade-off, okay? So pooling just reduces computational burden downstream. And you don't have to include pooling, okay? You can skip pooling and see how big your neural network, how many parameters your neural network has. For Conv layers, as we saw earlier, even if I have 10 filters, the number of parameters was 280, right? If I have 64 filters, it's just 64 times 28, right? It's not a big number. But what happens is the moment you start talking about a fully connected layer, each neuron will have a ton of weight, okay, ton of parameters, okay. And so if you have, let's say, 1,000 neurons there, like 1,000 hidden units, right, in that hidden layer, then you already are talking about 1,000. So for example, we saw, right, 1,000 neurons times 3072. Let's say if we vectorize the input image, CIFAR10 image, and if you do this, then these are the number of parameters. So it's already 3 million, right? So 3 million parameters just for a fully connected layer, which is directly talking to the input image. Okay. If it was, the question is, so this need not happen only at the beginning. Okay. So polling actually is very helpful, especially when you start going from Conv layers. So you'll see in the typical architectures, what happens is you apply Conv layers, and later on you start using fully connected layers. Clearly, when you try to get to scores, you will use a fully connected layer. Okay. And so those layers will actually take the bulk of the number of parameters in the network, in the sense that they have a lion's share of the impact on the number of parameters in a neural network. Okay? So you want to keep those fully connected layers somewhat manageable. And so pooling is one way, but there is certainly loss of information. Okay, it could be that 5 is important, as you said, and we may be losing information. And so our classification accuracies could potentially be dropped.
Yeah.
Could drop, sorry. Yeah.
Got it. And also you mentioned we slide 2 steps. So does it mean that stride is equal to 2 here?
Yeah. Stride is equal.
Yeah. Oh yeah, I did not see that. Okay.
Yeah. So I mean, these are not really filters and striding. Those ideas they apply clearly from the Conv layer explanation that we just saw earlier. but you can just think of just some sort of averaging or some sort of shrinking of compression going on here, in the spatial dimension. So yeah, you don't have, I mean, you can use formally, stride is 2 and filter out 2 cross 2 sides.
Okay. And also, does the zero padding concept work in this pooling as well? Because that was also one of the concept of convolution.
Yeah, I mean, you can, but if once you add zeros, at least for max pooling, it doesn't matter. But it just, generally what folks do is they generally have even sized input, weight and height. So generally they have something like 4 cross 4 or 64 cross 64 or something like that, and they generally divide by 2. That's what folks do. You can have max pool with filters of size 3 cross 3 or something else. Adding zeros, does influence things, as we saw earlier. But I haven't seen, from my limited experience, I've not seen people adding zeros. Okay. But certainly there's nobody stopping us from doing that.
Okay.
Yeah.
Thank you.
So yeah, I mean, I think this was written like, from my last year or something. Some folks are saying, hey, you don't need to do pooling at all. But it's just about, capturing the dominant signals and trading off computation and so on. So fully connected layer, I've been talking about it quite a bit. So let's, as I said, this is exactly what we saw in the feed-forward neural networks part, as well as what you implemented in your assignment 1. That hidden layer is exactly a feed-forward neural network layer, okay, fully connected layer. So I will not show this. I think I'm not sure if this link still works, but CIFAR10 is something that you will actually access and work on in assignment 2. And we have seen images of CIFAR10 before. So I would also just look at the assignment, look at the data set. One nice exercise you can just do is get CIFAR10 data, download it somewhere, and just use PIL or some of the Python imaging libraries. Okay, Python image handling libraries like PIL or I think Willow, or there are many others. Okay, to just view those images. Okay, so those images, as I said, it's just 32 cross 3. So you can just read the image and visualize it, okay, in Python in a Jupyter Lab notebook. It's a good starting exercise to do. Okay, so let me summarize for just this part. What we saw is the conv layer. So there's an extra new point here, which is that conv layer is basically taking into account, first of all, spatial invariance feature that was seen in image datasets. The neurons look local. They only look at local parts of the input, as in small regions of the input. But if you apply multiple conv layers, the subsequent regions. So if let's say there's a conv, let's say this is the input, and let's say this is a conv layer, first conv layer. Let's say some neuron. It looks at a small part of the input, but let's say conv layer later, it's going to look at a small part of its input. Okay, let's say small part of its input, but each of the neurons is looking at small part of its own input. Similarly, its own input. So this neuron is actually seeing a huge part of the input. Okay, so this is what I meant here by hierarchy of features. So it's just a very, I guess, intuitive sentence here. It's just saying that if you apply convolution layer, those neurons are, their receptive field is limited to a small region of their input, but original input, which is the image, few layers before, they probably are looking at a huge part of that image, and so they may be detecting, like a full face or a body of a cat, and things like that. Okay, and we'll try to see next, some debugging ideas about convolutional neural networks, and so we'll see how if they are interpretable or not. So any questions up to this point? If not, let me go to lecture. So the next set of slides. Well, sorry for scrolling, but yeah. So what we'll do is now continue with CNNs again, and Now what we're going to talk about is, hopefully, if not today, maybe in the beginning part of next lecture, we're going to look at what is called transfer learning. Okay, and this is where this is a big idea, not just with images, but also with text. Okay, where folks who have really good computational resources and access to really large scale data sets have already trained some good neural networks or some deep neural networks, generally CNNs or variations of CNNs, okay, for images as well as for text and equivalent classes of models. Okay, these are called, for example, I don't know if somebody has heard about GPT-3. I think earlier John was mentioning, I think a couple of classes ago, some new model by OpenAI for images. So folks with a lot of resources have trained models, and some of them have published the model weights, to the public. Okay, transfer learning is the idea of trying to use those model weights. Start with those model weights and adapt the weights to respond to better classification for your specific applied setting. That's the idea of transfer learning. The data set that you do a good classification or something like that on may not be the same data set that the folks from Google or Facebook or whatever, whichever research lab, for example, have used to get a model and therefore the model weights. Okay, that's transfer learning. So we'll talk about it. This is the most important thing. But first, let's look at visualizing CNNs and getting a sense of how to debug whether they're actually picking up the right signals in images or not. And that will tie back to this spatial invariance and the different things that we talked about just now. Okay. And then I think next we'll talk about this part next lecture. There's no need for recap. This is about parameter count. I would suggest folks to look at this slide to just get a sense of parameter count, but I'll not repeat that here. And not backpropagation as well. It's just the same idea. So W, B, instead of that, you have filter weights. They also need to be updated using gradient descent. Okay. So let me now directly talk about visualizing CNNs. Okay. So although this subtopic says visualizing CNNs, it's all about just some intuitive model diagnostics that you can perform once you have a trained CNN model. Because the training a CNN is, so just like you did, train the Keras-based, two-layer feed-forward neural network model, right? Training a CNN would be very similar. Okay, so there are instead of sequential, instead of linear layers, you can have con 2D or whatever con layers. Okay, in Keras, for example. And you can train it, okay? But once you train it, can you interpret, can you get a sense of, hey, what is the CNN doing? And is it picking up the right signals? Common criticism is basically you have a bunch of weights and you have a neural network with, let's say millions of weights. It's unclear what it's doing. Okay, maybe it's classifying the dogs versus cats correctly or the road versus grass correctly. But what features is it actually using? Okay, something like feature importance or something like that would be helpful. So we look at a few attempts to just kind of do post hoc, post hoc. I would say post hoc just means post training, poking around the neural network, poking around the CNN to get a sense of what it learned. Okay? So there are a few things that you can straight away look at, which is activations. Activations are just the outputs of the layers given training data, for example. So activations are just the outputs of the layers after nonlinearity, right? So you can look at all your training data. How do the activations look like? That's the first type. You can look at the weights. So the weights just mean you can look at the weights of the fully connected layer, or you can look at, which is hard to kind of interpret anyway. You can also look at the filter weights. Okay. So that's the second type of post hoc inspection that you can do. Third thing you can do is you can look at the images in an embedded space. Okay, so this is just very similar to dimensionality reduction, where you don't directly dimensionally reduce the image themselves, but we'll talk about what do you embed. Okay, so what do you reduce dimension of? Okay, we'll actually be reducing dimensions of some vectors. Okay, not the original input image itself, but what is that vector? Okay, and the most important thing is this notion of embedding or embedded space. The next idea is to see, hey, if the image is detecting a cat, if I now take that image and remove that cat portion of the image, okay, and maybe change the pixels to all black or something. Does the image still say it's a cat? If it is, then it's picking up some other signal in the image to say it's a cat. It's a cat. Okay, so that's the use of occlusion to kind of get a sense of whether your CNN is working well or not. And finally, you can also look at, hey, what are the images in my training data which are activating certain neurons or getting the highest score from class, to get a sense of, hey, is the image is the neural network doing picking up the right is doing the right classification, picking in the right sound. Okay. So I explained that in a very quick way, but we're gonna look at each one of them in a little bit of detail. So is the goal clear? We just want to look at we just want to post training inspect trained CNN. So this is something that we just saw. So if you look at, so activations, as I said, activations are just the outputs of any layer. So any of those tensors that we were talking about, okay, as long as we have done the nonlinear operation as well at a neuron level, then those are called activations, right? Now, what we can do is, if we have a trained neural network, we can pass an input image. We can pass. We'll typically have lots of images which are in our training data, right? So we can pass our input image. So let's say, for example, we can pass the input image of a cat, and then see how the activations at different 2D activation maps look like, or different depth slices look like. So like the first conv layer here, it seems to have so many depth slices. You can look at, hey, some depth slices are detecting some patterns, right? So you can visualize that, and you may see that some depth slices are never going to is always black. Okay, so by which I mean that, let's say I passed the first training image and this depth slice was black. I passed the second training image, this depth slice was again black, and I passed let's say the 1000th training image, and it's still black. Okay? Which means that the activations are all 0, which means that, let's say we are using ReLU activation, which means that there is no, like, it's not doing anything, right? So that ReLU, if you remember, it's max of 0, x, and the output is 0. That means that x was it was most likely negative. Okay, so this is basically like a dead filter, right? It's not really producing any signal on any of your training data. Okay, these are some things that you can detect by just looking at activations, or if you not visually look at them, you can look at histograms of activations, right? Histograms of activations you can see even for fully connected layers. So the feed-forward networks that you're working with, you can look at, hey, how do the activation distribution looks like? Does the activations are all close to 0, or are they nicely spread out, for example? Yeah, so that's about activations. There's not really much to infer here, but except by trying to debug if there are, like, some filters which were initialized in such a bad way, or they are just useless, that they're not detecting any signal. Okay. Any questions about this part? Okay, let's move forward. So you can also look at, once you have to train CNN, a convolution neural network, it could have, and I think Supriya asked earlier, what's the sequence of layers, right? So we haven't been talking about sequence of layers. So generally, I think in the example we had 2 con layers, and then a fully connected layer, and then we're getting scores. Okay. But this is something that you get to choose. There is no, I guess, set way. Certainly, the popular architectures have some pattern of how these layers are connected with each other. Okay. Anyway, visualizing weights. So if conv layers, we know it's a set of filters. For fully connected layers, we know it's the weights, the W matrix and the bias vector. For conv layers at the beginning, we just saw an example in LXNet, right? So if the conv layer was right in front of the input image, its depth is 3, so you can actually visualize, like you can visualize how the how the filter itself looks like, filter weights, themselves look like, because they are like an image. Okay. But the moment you go like to a second conv layer, a third conv layer, and so on, it's hard to visualize anything. You can see here they have tried to plot slices of each filter. Okay, so some black and white images, but yeah, I mean, it's very difficult to make a good sense of what the weights are. I mean, certainly you can look at, hey, some filter weights are all close to 0, or are all same values, something like that. You can figure out. Okay, but it's very hard to do, because now you have too many such filters, and except for the first conv layers, it's generally hard to interpret the later layers this way, at least. Okay, so two techniques, they don't seem to be that valuable. The next technique is interesting, is actually pretty valuable, and something that a lot of people do, okay, here with especially with CNNs, is to embed so embed your so once you have a trained CNN, you have an image and you can get scores, right? But what we're going to do is pick the last activations before which you get scores. Okay, so for example, the scores. So remember, in a CNN, even in the example that we saw, scores, there was this fully connected layer before that, right? So the fully connected layer was producing a some activation vector, okay, which when multiplied with a W on B matrix, this W has to have, let's say if it's a 10 class classification, then the W should have 10 rows, right? Now this A is basically, is called an activation vector, and that's the output of neurons at that layer, right, at the previous fully connected layer, and that's and H is called the pre-activation, by the way. So you can look at this activation vector as a representation of the input image. Okay, so not the score vector, but the activation vector. So let's say I have a training image. I pass it through the CNN. I store this activation vector, okay, for each of the images, each of the input training image. Then I can pass this training images on the trained CNN, right? So now I can get these activation vectors, and they are representations of the original input image. They are like the vectors which represent the original input image. Okay, and these are also called, I guess, embeddings. Embeddings just mean vectors in this case, embeddings of the original input image. For a single image, it's just an embedding. Okay. Now, what you do is just think of doing PCA. Remember, from some of you who have done 572, if you have a feature vector, you want to get a sense of, hey, do these, you have feature vector, and let's say you have a 2 or 3 class classification. If you project down this 10-dimensional or whatever dimensional feature vector into 2 or 3 dimensions, you get a sense of whether things cluster. Okay, same vectors which belong to the same class, do they cluster together or not? Okay. So for example, and that's something along the same lines, we do an embed, we project these embeddings or these vectors into, for example, a 2D space, okay, 2D or 3D. And these embeddings generally should have this operation of going from a higher dimensional space to a lower dimensional space. It should not be some random, like you cannot just chop off like the third coordinate onwards and just look at the first 2 coordinates to get a sense of whether the input image has good representation or not, right? So what you do is you pick some techniques which try to preserve some properties. Like if two vectors in, let's say, the 10-dimensional space were so far apart, then even in 2-dimensional space, they hopefully are far apart. And if 2 vectors were close to each other in the 10-dimensional space, they're close to each other. Okay. And there are some techniques which try to preserve this distance property. One of them is called TSNE. Okay. There are many techniques here. TSNE is one of them, but you can think of this as a replacement of PCA. It's just think of this as nonlinear PCA for our purposes. But the idea is that if you can get these vectors for each of your training images, and then you project them into 2 dimensions, and what you do is you'll get 2-dimensional points, right? Points in a plane. Then at each point, you just replace it with this image, okay, the image that corresponds to that two-dimensional point. And then, and this, you can get a collage like this, okay? And you can see that, for example, maybe similar images are here, and maybe something, circular clocks are here, and so on, okay? So this tells you that the CNN or the neural network has learned the right representations of the input image. Not the right, I would say, good representations of the input image. Okay. So because images which have similar features like clocks here then have, because they are close to each other in this 2D space, maybe their vectors in the 10-dimensional space or whatever 1,000-dimensional space, actually 4,096 dimensional space in this original CNN from 2012, from one of the popular CNNs from 2012. Maybe in the 4,096 dimensional space, the vectors are also close to each other. Okay, and this is a property that says, hey, the CNN did learn to kind of represent, let's say, all the clocks with similar vectors, all the maybe, I don't know, like scenic photographs using similar vectors and so on. Okay, so that's an indication that the CNN has learned something, non-trivial, okay, in terms of discriminating classes. By the way, this is, I think, for image net, I think. And so that's why you see a lot of classes here. You can do the same for even, for example, CIFAR10. Okay. I don't think I have time for occlusion. Occlusion is also a very interesting, clever idea. We'll pick this up at the beginning of next lecture. Okay. At the beginning of next lecture, the important thing will be, just finish up this type of informal model diagnostics for CNNs and talk about transfer learning next time. But since we're running out of time, I wanted to pause here and check if there are any questions about what we have done so far, and if there are some parts which are confusing or where we're heading next.
Professor, the page number 14th, I did not understand. Could you please explain again?
Yeah, I was just saying that, so CNNs, any neural network, any model is going to take an input and produce scores, right?
Yes.
Now what I'm saying is, hey, this score was actually, if you just expand it out, just the last part of this model is some weight matrix times max of 0, h. Okay, let's say we are using ReLU nonlinearity plus some bias, right? So that's what a score vector, I mean, even in your assignments, this is what you did. Okay?
Yes.
Now what I'm saying is, if you take this max of 0, h, you can just call it A. These are called activations, by the, these are called activations for any layer anyway, any layer's output. But just take these are penultimate layers activations, right? Penultimate because score is like the last tensor, and the tensor before it, the tensor before it is basically this activation vector. It's basically, since it's a fully connected layer, you just get a vector anyway. All I'm saying is, for each image, image 1, there's going to be A1, image 2, there's going to be A2, image 3, there's going to be A3. Okay, so these are all going to be, for example, that AlexNet model had 4,096 dimensional vectors. These activations were 4,096 dimensional. They just happen to be that size. Okay? These are all vectors. So all I'm saying is, these vectors can be considered as representations of the image. Okay, so image we have, like, for example, for CIFAR10, we had 32 cross 32 cross 3 size image. But if you think of it this way, if you had images and their labels, what you can do is take the images, get these activation vectors, and forget about the images, and take these vectors and the labels as like a training data set. For example, you can run logic regression, you can run SVM. It's like a data-driven feature engineered feature vector for each image.
Oh, okay. And also, what is H there?
H is just the pre-active. It's called the pre-activation. It's just the vector before you apply the ReLU nonlinearity. So you have the pre-activation vector. It's just the hidden layers output. It's just a neurons output before the nonlinearity operation is applied.
Okay.
The neurons output before the nonlinearity is applied is just a linear combination, right? It's like whatever is the input times element-wise multiplication plus some bias, right? That's what H vector is.
Oh, okay.
It's just the hidden vector, basically, before doing the nonlinearity.
Okay, got it, Professor. Thank you.
Yeah, I don't think even we needed to expand this way. We could have just said, hey, S is equal to W times some input plus B. That input is what is what I'm calling as a representation of the input image. It need not be the only representation, by the way. You can take any layer. So we have input image. You can take any layer. You have a tensor. That tensor is a representation of the input image. Okay. But we're just picking the last, the last tensor, last but one tensor, and that tensor happens to be a vector because that's a fully connected layer there. And so we're saying that we're just calling that to be the representation input image.
Okay. And I have a question regarding assignment. If suppose anybody has any questions regarding today's lecture, I'll ask after that. Yeah. So I mean, we are already like hitting the time limit here. So we'll talk about, just to summarize for this part of, after the break, we were just looking at, hey, we have a trained model. We looked at pooling certainly, but we also said, hey, if we have a trained CNN model, then how do we get a sense of whether it's working or not? And I would say, hey, we could look at activations to get a sense of, hey, are the parameters, even outputting anything, okay, non-zero signal. Or you could look at weights themselves to see if the weights change from the beginning, or if the weights are all zeros or things like that. And the last thing we saw is that, and which is an interesting idea, and this idea is something that people do quite a bit, is to, if you have a trained CNN, take all your training data, training images, sorry, just the X, the images part, not the class labels. Take the images, pass it through your trained CNN, you'll get these activation vectors. Now, project these activation vectors down into 2 dimensions, okay? For example, like this. You get the 2-dimensional vector for each of the bigger vector, 4096 dimensional. But then you can also replace the image there, right? So just to get a sense of spatially, are images which are supposed to be of the same class close to each other in this lower dimension. You can visually see it. So that gives you hope that, hey, if the projection operation was nice, that it preserves distances, then hopefully the 4096 dimensional vectors were close to each other if they were in the same class. Okay. So that's what we saw. And we'll continue from here next time. Okay. And next time we'll be looking at transfer learning as a key idea. Thank you, everyone. I think we went over a minute there. So folks who want to stay back for questions regarding assignment 1 or questions regarding what we discussed in this lecture, they can stay back. For the remaining folks, I'll see you next week.
Hi, Professor. This is Chetnia. I have a couple of questions from today's lecture. We discussed about stride, right? Like to move like one column by column or at the 2. So is it like when we have the image and when we want to like predict the image like exactly as is, like you showed us like we had like blur, we had outline type of filters. So when we want to do like exact prediction, we use stride of 1 because we want to like look at each data point. Is that how it works? And for a blur image, it is not necessary that we go through every set of points like with 1 distance. So at like a blur filter, can we use like a stride higher rate because it is not necessary at a pinpoint detail?
That's a good question. I actually don't know whether for certain types of filter, like first of all, these filters are data driven. So we cannot, so post hoc, we can say, hey, maybe this looks like a blur filter, or maybe this looks like a sharpen filter in the deep learning case. Okay, but a priori, because you need to specify about how your conv layer performs. Okay, even before these weights, out the weights using by minimizing loss function, right? So a priori, I would say you need to still decide whether you want to take stride 1 or stride 2 and so on before even talking about, hey, this filter could probably be blur filter or not. Okay, but yeah, you have some intuition about, hey, if I was using blur filters, then maybe I just need to take stride 2 because I don't need they already averaged, and so I don't probably need overlapping patches. That's what's happening, right? If stride is 1, there's overlapping patches of certain degree.
Yeah.
If stride is 2 or 3, then you're like not, now you're kind of getting less and less overlap, basically.
Yeah.
But I think you need to decide that a priori, and a priori, no filter has a specific name in at least in deep learning, at least in our CNN model, right? It's just you pick arbitrary weights, but you do gradient descent, and those weights happen to turn out to be, some happen to turn out to be like blur filters, some turn out to be happen to be, sharpen filters or something. That can.
Okay.
Yeah.
And in this image, like the one, is it like the output after our algorithm neural con network runs, or is it the prior image which we give and where it shows like which are near to each other, like that embedded image?
Sorry, you're talking about what we just saw, right?
Yeah, the low dimensional embeddings,
yeah.
The college. Yeah.
Yeah.
I wanted to understand if this was like the output of our after our algorithm for con runs, or is it like the before input?
So think of it as 3 stages. Two stages, sorry. In the first stage, you did gradient descent, just like what you did in your assignments. Okay, you did gradient descent to figure out the parameters of your neural network. This neural network happens to have a con layer and let's say fully connected layer and so on. I just said, so you have a bunch of collection of parameters, each, let's say, parameters per layer, that's fine. You first do gradient descent somehow. Like, for example, in Keras's case, you know how to do it, right? So you train so you do that and you get the trained CNN model. Okay, trained CNN model will have some layers. Let's say con, like I think in here, this one, not this one. So here you can see that there's a con layer here, and there's a con layer here, and there's a fully connected layer here, fully connected layer here, right? Therefore, con followed by con layer, and then fully connected layer and fully connected layer. So you train it first, okay? Once you've trained it, actually, this is a good example here. Once you've trained it, what you do is you pass all your training data, okay, different force. You may have, in your training data, you may have different force, right? Like in MNIST.
Yeah.
You have like 10,004 values or something, 4 images or something. For each one of them, there's going to be this vector. Okay? The last vector, not the score vector, but the one before the score vector.
Okay. Yeah.
Collect all those, these vectors, activation vectors, and these are what I'm calling as embedding.
Oh.
Embedding of the image.
So, okay, all these activation vectors which look alike will have same score, so they'll all be like together. Yes. At one place. I
mean, yeah, if they're similar activation vectors, hopefully they'll have the same scores because it's a linear transformation going on, right, at the last layer. After activation is just WA plus B. So it's not, there's no nonlinear, there's no crazy stuff going on there. So if the activation vectors are similar, then yeah, they'll get the same score. But what we're trying to do is that, hey, this activation vector is too big. We can't visualize it. Let's project it down. But with projecting down operation, you can think of PCA, basically. For example, if you want to do a linear projection. But instead of PCA, the techniques that folks use is, one of them is called TSNE, stochastic neighborhood embedding or something. There are some techniques like TSNE, and there are a couple of more multi-dimensional scaling, I think. So those do nonlinear projections down. Okay? And so once you project down to 2 dimensions, if the images could be close to each other, you can visually see that. Sorry, yeah, something like that. Right, you can maybe zoom in and see like landscape figures have similar 2-dimensional projections. Yeah, same thing. You can look at different classes here. Yeah.
And one other question I have is, like, we discussed about pooling, shrinking, right?
Yeah.
So PCA is something similar. When we have like 20 column vectors, like we do like 3. So can we do pooling here instead of PCA?
Where are we doing pooling?
I mean, like, not sorry, I think I framed the question wrong. So when we want to downsize something, can we use pooling? Is what I wanted to ask.
You can, but it's a very crude operation. So pooling is not doing, so PCA is just a linear transformation, okay? So even max pooling is not really a linear transformation, it's a nonlinear transformation. But if you take average pooling, for example, it is a linear transformation. The PCA is a linear transformation which is optimized for something, okay? It's trying to capture the highest variance in for example, input matrix, right? So or train data or input data. Whereas let's say average pooling, it's also a linear transformation at the end of the day. Okay, it's a linear transformation. It's like you get a 4, you get a bunch of numbers, maybe more numbers, and you get a bunch of smaller numbers. But that may not be optimized for capturing, let's say variance of the data. Right? It will not probably be. So in that sense, it's not a good, I guess, projection operator, a good dimensional reduction operator. But it does, okay, it does coarsen the input data, which makes sense for images because at higher levels, I would say, for example, at this level, whether this, this matrix, you can see it looks pretty much similar to this matrix, right? This has been downsampled.
Yeah.
Similarly, this has been downsampled. It looks pretty much the same as this image, for example, right? So, so downsampling in this case, by doing just pooling is fine. But if you are thinking of preserving some properties of the data like variance and so on, then PCA and nonlinear variations of it are a better choice. Actually, at this point, let me stop recording. I think, but thanks for the questions.